Okay, then we'll start. So just as a brief recap, last time we did overview of dark matter models. Discussed how we know that dark matter is a cold fluid back until redshift about 10 to the 6 slash temperatures of keV. And today we'll talk about thermal candidates and specifically go to the sub-GeV mass range. So I forgot something I could have done something I'll do while we're waiting for people to trickle in is just briefly remind you of all the standard thermodynamic quantities that we'll need. So I'm just going to leave them up here. We have our phase space distribution. Okay, I don't remember this number. So I'm just going to keep them up on the left side so that we'll have them handy. Okay, and the number in the bracket is the factor I need in front for fermions as opposed to bosons. So that's our number density and our energy density. An important quantity we'll be dealing with is the entropy density.
I'm sorry, did I somehow miss the definition of squiggle of 3?
Zeta of 3. Okay. It's a bad zeta. So our entropy density, by the time I walk here, I always forget what these numbers are, so correct me if I'm wrong.
So what is zeta? Like that's a function?
It's just a zeta function, yeah.
Duh.
Just a number, like 1.2 or something.
Right, I'm sorry.
Nope. Okay, so our entropy density is given in terms of, so all of these have some degrees of freedom here. And then our entropy density is given separately in terms of this G star. So it's related to our degrees of freedom, but it just accounts for the fact that we have different factors for fermions and that different things can, different species could have different temperatures. So let me just make sure I get it right. So we'll sum over whatever species there are in equilibrium, or whatever species there are, period. And weight it by their relative temperature and whether it's a fermion.
So what does the S stand for?
Just to help remember that it's related to the entropy density. I think different people sometimes use different notation. I just picked, I think this is the one that maybe Kolben-Turner uses. Can't remember. Okay, so everything here I've written is for relativistic species, and I've dropped all the chemical potentials, or assumed that it's small, and that's what we'll be dealing with.
So the mu in that first one is not the chemical potential?
That is the chemical potential. I'm setting it to 0, basically. Yeah. And if let me also write down, just to remind everyone, our W metric. Probably went through this already. And the Hubble expansion rate tells us the rate of growth of the scale factor. And remember that Einstein's equations tells us that h squared is related to the energy density. And G Newton in natural units will be 1 over m Planck squared. And the energy densities are t to the 4th. So a helpful thing we'll use throughout this lecture is that the Hubble expansion can be written approximately as there's a g in front times t squared over m Planck. Okay, and now we'll set, again, like I said last time, our horizon size, our expansion rate. It's the most important quantity we need to keep track of.
I've never seen that definition of H equals G2 squared over M Planck. Where does that come from?
It's only in the radiation-dominated era, so I'll write that down just to be clear. When rho can be replaced by the t to the fourth. Thank you. Squared of g. Oh, here, yes. Sorry, there are too many g's. I thought you meant this one. I got confused. Okay, I agree, yes. Yeah, I took the square root of rho, so yeah. And there's a order one factor in front. That's about 1. Forget about it. Okay, so I'm going to briefly cover this up and show or draw the evolution of this quantity, G star, the degrees of freedom weighted by the temperature. So as is kind of standard in cosmology, sometimes I'll put time running to the left, so temperature going up on the right. This is GV, let's put MEV, and somewhere up here, TeV. So as we look back in time, we have more and more degrees of freedom in equilibrium. So we start somewhere here. Quantity is around 4. At around an MEV, we have E plus E minus. We have some other muons, pions, and stuff here. The QCD phase transition, we get a big bump, and then more small bumps up here. Final value is about this. Okay, so the reason I've drawn this is because when we're in when we consider thermodynamic equilibrium, we consider all the particles in equilibrium. The entropy, the total entropy is conserved. So this is an entropy density. So for the expanding universe, I have to write a cubed S. This is a conserved quantity. And so what happens every time we go across these thresholds where there's more particles is we increase, well, let's do it the usual way. As we go from high temperatures to low temperatures and we have a freeze out of some species, so there's E plus E minus, and they're in equilibrium, but then we don't have the temperature to produce them, so they're gone from the thermal bath. And at each of those steps, G star changes, and so we have to remember that the temperature does not just redshift across that transition, there's also a change in temperature such that the total entropy is conserved. Yes?
I haven't really processed this before, but looking at that, it looks like essentially in early times, everything's in thermal equilibrium. So Ti is going to equal T for pretty much all of the species.
Yes.
And so in order to have, at around TeV scale, a G star of 106-ish, you're going to need something like 106 species total.
Yeah, that's counting all the standard model degrees of freedom and assuming they have the same temperature.
Yeah.
Yeah.
So like how many species do you, I mean obviously there's multiple degrees of freedom so that's not quite right, but how many species are there or that early on to create that number? 6.75.
Yeah, that's a standard model. I'm counting.
All of those?
Yeah,
Okay.
everything that we
I didn't
know.
realize how big a number that was going to get.
Everything we know, assuming just the left-handed neutrinos. Yeah.
Okay.
Yeah, and that will play a role again in the next lecture when we talk about, people talk about constraints of an effective on dark matter, and it will matter when the dark sector freezes out because of this change in the degrees of freedom in the standard model thermal bath. Okay, so this is all still just setting the stage. There's two more quantities that I want to write down that we'll use throughout. One is the energy density of dark matter today. So these are today. And it's about 10 to the minus 11 eV to the fourth. And also I want to write the entropy in the photons today is about 10 to the minus 11 eV cubed. And the fact that these are basically the same in this unit actually reflects the fact that matter radiation equality occurred at a temperature of around an eV. But that makes it very convenient because they're basically the same number with this eV to absorb the units. Okay, so having this set up now, what I want to do is first we're going to use this and review thermal freeze-out of a relativistic species, similar to what was done yesterday. Then we'll do non-relativistic species, all pretty fast. And then we'll use that to start motivating different models and getting to sub-GeV dark matter. Okay, so let's start with relativistic. And the goal of all this is to be able to do these estimates in a quick way, similar to what you would actually do when you're starting out some sort of project and deciding if it works. So if you're not following anything, definitely stop me. So for the neutrino case, neutrinos are kept in equilibrium by processes like this. They can annihilate to E plus E minus and back and forth. And while they're still in equilibrium, we have this equilibrium number density. But as we know, this process can drop out of equilibrium. So the quantities we want to compare are always the rate of annihilation, or whatever the relevant process is, compared to the Hubble expansion. And the rate of this process we can estimate using the fact that the number density is T cubed. This cross-section we can estimate by using the fact that first this process is happening, if this process is happening below the Z mass, then it's going to be 1 over mz to the fourth. So you can integrate out the Z and it'll create a dimension 6 operator suppressed by 1 over mz squared. So the total cross-section should be 1 over mz to the fourth. And then because it's a cross-section, we put back in a T squared to make it an inverse mass squared for the units. And we can compare this rate now with Hubble. So this is time goes to the right, which I can also track by 1 over T. So this rate of annihilations goes as T to the 5. So here it is. I'll just write it like this, draw it like this. This is gamma. While the Hubble expansion goes as T squared. So it doesn't drop as fast with time. And this is what we usually identify as decoupling or freeze-out. And the rationale is that, again, the rationale is this sets roughly the age of the universe at any given time, or the horizon size. 1 over h sets the age of the universe. And so if we multiply that with a rate, that will tell us how much the number density of the neutrinos is changing. So it can, assuming this process is kinematically allowed, the annihilation will continue to happen. It's just that the number of annihilations per neutrino becomes much less than 1. So setting this rate equal to the Hubble expansion, I get that the temperature is 1/3 the power of mz to the 4th over m Planck. And this, we can plug in some typical numbers. If this is around, it doesn't have to be exactly mz, but around a TV to the 4th is about 10 to the 12 GeV to the 4th, and then, or 10 to the 16, and we divide this by m Planck. We'll get of order 10 to the minus 3 or 10 to the minus 4 GeV, and then we take a cube root. It'll be close to 0.1 GeV or so. Or, sorry, let's write 0.01 GeV to be a little closer. So it'll be around an MeV, and that's, or a little bit above an MeV. Okay, and that should, hopefully that agrees with what you remember about neutrino freeze-out. So this tells us at that temperature, the number density was, the number density at that point doesn't change due to annihilations, but it does dilute due to the expansion of the universe. So the number density today would be the one at freeze-out, scaled by some, well, scaled by the scale factor. And normally we could use, well, sorry, typically we could use the fact that the photon temperature also redshifts as a scale factor, except for across those decoupling transitions where we have new degrees of freedom or degrees of freedom going out of equilibrium. So instead of using the scale factor, which is a little bit annoying to keep track of, we keep track of the, we get the number density today by using the entropy density. So in other words, the entropy density times the scale factor cubed is conserved. So if we just track the scale factor at the time of freeze-out and the scale factor today, then we get the correct we can get the relic abundance today. So this motivates the definition of this y variable, which is the number density divided by the entropy density. And this is constant because both of these scale the same way. It's constant after freeze-out. And we see that y for the neutrinos at freeze-out will just be roughly, ignoring all the factors, will just be g times t to the cubed over g star t to the cube. So it's going to be an order 1 number given by the ratio of the degrees of freedom. Now the thing we want to satisfy is that, well, okay, so to get the energy density today, we take this quantity, Yeah, we take this quantity, this is the number density, and we multiply it by the mass to get an energy density, and then we multiply it by, this is the freeze out, and we multiply it by the energy density today. Both of these quantities I just gave you over here for a dark matter candidate. So I'll write one more relation here, which you can directly see from there, which is that whatever the freeze-out co-moving number density is, it has to satisfy that, or it has to be equal to EV over the mass for a dark matter candidate, for something that's 100% of the dark matter. Okay, so this relation makes it very, very straightforward then to start to estimate estimate your relic abundance of a dark matter candidate in kind of the natural particle physics units. And we see what was mentioned yesterday, which is that now let's take the case for neutrinos. This co-moving number density is just order one number, so I'm just going to drop it, and then I get rho today is equal to the mass times the entropy density and anything that's heavier than an EV will produce way too much dark matter. And as was also discussed, the neutrino mass is bounded to be about less than 0.1 EV, roughly. And so we also know that the neutrinos are a small fraction of the total energy density in the dark matter.
Sorry, so that rho today is, the used rho, is that's for neutrinos or dark matter?
Yeah, sorry, neutrinos, I'll put that. Or anything that was relativistic.
Do that calculation separately for each flavor of neutrino that had a different mass, or?
Yeah, so you would sum up all the masses here. Mm-hmm. Okay, so that's the lesson from freeze-out of a relativistic species. We know that something has to happen to start depleting the dark matter relic abundance. We learned last time if whatever the dark matter candidate was, if it had a similar temperature as the photons, it should be heavier than about a keV, and that would definitely be way too much dark matter. We need something to dilute the number density of a thermal species, and so we'll go to, very quickly, freeze out of a non-relativistic species. Why is the, sorry, could you specify, you mean?
Yeah, because they use the photon entropy.
I'm using the photon entropy to track, what's that? Yeah, to track the evolution of the scale factor. So the ratio of the entropy densities in the photon is related to the change in the scale factor. So I can rewrite, so this was so you agree with this one. And then I can rewrite this using the fact that entropy times A cubed is constant. I can rewrite this as S today over S freeze out. So that's the relation I'm using.
I think the question is, why is it S gamma as opposed to S total? Why is it just the radiation entropy as opposed to the total entropy?
I want to use the radiation, I'm using the radiation density because I'm tracking everything that's in equilibrium.
Okay.
Yeah. There is, if you're wondering, there is a contribution of neutrinos to the total entropy density today that's model dependent because we don't know exactly what the neutrino mass is, for instance. Yeah. Yeah, so first the neutrino, even if the neutrinos, well, given that the neutrinos could be relativistic today, they still have a lower temperature and the contribution to the entropy density is small.
So here, we can consider the end of the still
Yes, at the time of freeze out, it was relativistic, so I used the number density as T cubed for neutrinos. Yes, the neutrinos could be non-relativistic today, but still their number density would be given by T cubed because nothing is changing the number density and it just dilutes with the scale factor. Yes.
You say nothing is changing the number density, but strictly speaking, neutrinos are produced, for example, in stars. So what you're saying is
Yeah, negligibly.
The relic density, the stuff that's left over, is not changing.
Yeah, effectively it's any change there is very, very small. Yeah, exactly. Okay. So let's draw a similar diagram for a dark matter candidate. And I'll put maybe a z here. I'll just put a question mark or some new vector. And I'll get into specific possible portals with the standard model later. And annihilation to some standard model fermion, which is much lighter than the dark matter. So the very quick way of getting the Rollick abundance in this way, we're going to skip the Boltzmann equations, is again by relating the annihilation rate with the Hubble expansion. And it's gonna be off by orders, a couple of order 1 factors, but it'll be enough for what we're doing here. So this has some cross section, which I won't specify yet. I'll get to that in a minute. And I want to look at when this starts to decouple, and at that point, the dark matter is becoming non-relativistic. So the number density is dropping. So let me just put nx here. And I'm not telling you anything about either of these quantities yet, but I'm going to relate it to H, the Hubble expansion for freeze out. The next thing I use is that this co-moving, this y quantity, can be written. It is just the number density at freeze out over the entropy density. And the entropy density is known. So it's going to be something like this. And the number density can be written in terms of the cross-section using the first relation. I'll just write sigma. Okay, so without really saying anything about the non-relativistic behavior of this number density, I'm just going to immediately replace this dark matter number density at freeze out with what it has to be by the definition of freeze out in terms of this cross-section. So I'm probably going to ignore all these G stars in the end, but we'll see. Okay, so now I have Sorry, it's all the way down here. I have, that was a very quick and dirty way of getting the freeze-out relic abundance for non-relativistic species. The part where I have to use some intuition from the fact that I have to make some guess is what is T. And we heard yesterday that T is going to be around somewhere below the dark matter mass. So we know that when T is much greater than the dark matter mass, of course, it's still relativistic. That's not going to help. But once the temperature drops below the dark matter mass, there's kind of an exponential suppression in the number density of dark matter. And so we know this temperature has to be just a factor of few, okay, it's order 10 or 20 below the dark matter mass. And so we can go ahead and replace all those T's with mx over 10, let's say. So continuing up here. Yes.
Is the reason why you put in this square root of g in the nominal relativistic case, but in the relativistic case there's none of this?
I apologize. Sometimes I drop the square roots of g because it's always like, it's often like 2 or 1. No, yeah. So, okay, so that's our freeze out y, and then let's say we want it to be all of the dark matter, then we use this relation that the freeze out y should be an EV over mx. No, that was completely general, saying that rho dark matter should be equal to whatever the freeze out thing is, scaled today and multiplied by the mass.
Okay.
Yeah, that was for dark matter candidate. So going back here, I set this equal to an EV over mx, and this is sorry. Let me make sure I get my, yeah, sorry. Here's EV. Forget thermal averages. Okay, so from that relation, that tells me what the annihilation cross-section must be in terms of M Planck. This EV basically, again, comes from matter radiation equality to give us how much dark matter there is. And this is about, again, 10 to the 19 GeV, so 10 to the 28. Well, let's write it like this. This is about 10 to the 19 GeV, and EV is about 10 to the minus 9 GeV, or is. So at the end of the day, we get that the annihilation cross-section has to be about 10 to the minus 10, well, 1 over 10 to the 10 GeV squared. Again, apologize for dropping all the G's. I don't want to keep writing them, but they're there. Well, let's put in the factor of 10. This will be 10 to the 9. This is the same quantity that Dan introduced yesterday, but just in natural units, such that we can start comparing with specific models and their cross-sections. Okay, so And let me use this. And probably you've seen by now that this is sometimes called the Wimp Miracle, because you can rewrite this set of numbers as roughly alpha weak squared over, say, TeV squared. Okay, so that was the review part. And we established that thermal freeze-out with annihilation of a non-relativistic species is good for getting the relic abundance. And we want to get this cross-section wherever possible for thermal freeze-out. In the next part, I'm going to start focusing on what this means for different models of dark matter. So let's take that process up there and just be a little bit more specific about the behavior of the cross-section. Again, I will probably drop a couple of order 1 factors. So I have 2 cases. Let's first take the case that this mediator in the middle is much heavier than the dark matter. I'm also going to allow for these 2 couplings to be some generic GX and some generic GF, just so that they can be different in principle. So the cross-section when this mediator is heavy is again estimated. First we have the couplings, and is estimated using the fact that it's an effective operator suppressed by mv squared. So the cross-section should go as mv to the 4th in the bottom due to the suppression in the operator. There should be a t squared on top. But since we're always looking at the process near freeze-out, I'm just going to replace the t squared with mx squared. Okay, that's very similar to the neutrino case. Okay. We next want to consider the possibility that mv is much less than mx. So in this case, the amplitude will have, the amplitude will have in it a s minus mv squared propagator. Dropping the other stuff here. And the center of mass energy, this s, is going to be of order mx squared. So by definition, we can drop this term, and we can just have a 1 over mx to the 4th instead of 1 over mv to the 4th in our cross-section. So replacing this with mx to the 4th, I'm just going to get something that depends on mx squared. Okay, and there's another process that matters now if I take this limit, right? Do you know what it is? Taking the vector to be much lighter than the dark matter now. Too many voices at once. Well, yes. Decay to the vector. So I still have the, it still has to be dark matter with vector. Yeah, I can radiate off extra vectors.
And just annihilate into vectors.
Exactly, yes. I can annihilate directly into the vectors now. So all these other effects will matter, but probably the most important one that we're missing is that I can annihilate directly into the vectors as well. So I'm going to have to cover that a little bit. So this is process A, and there will be process B, which is something like this. There you go. And if I assume that the vectors are much lighter than the dark matter, the only mass scale in the problem is the dark matter. So the cross-section will be similar, except for remember that these couplings are gx instead of gf. So I'm going to write it as gx to the fourth over mx squared. This is xx to ev. Okay, so now let's use these few estimates and draw some conclusions about when thermal freeze-out happens. Okay, the first thing we can notice from our equations here is that let's first consider the case where all the couplings are of similar order. So let's ignore the fact that gx and gf could be different. All of these cross sections will be saturated at around g to the fourth over mx squared. All right, so even the first case where I have an mv to the fourth is less than this because I've assumed that the vector is heavier than the dark matter. And I can take this g to be approaching 1. And if I set this equal to 1 over 10 to the 9 GeV squared, that gives the perturbative unitarity bound we talked about yesterday. So this is the Grieston-Kamiankowski bound for S-wave annihilation. Sorry, this is mx squared. Which is that as this is roughly how the cross-section scales, and as I take g to 1, then mx should approach the square root of this number, which I'm a little bit, I'm getting about 10 TeV, but these are all just order 1 estimates. It should be about 100 TeV. Okay, so that's coming from the fact that we just, it's hard to get such a large cross-section because of the general scaling of the cross-section.
So I've been assuming that little g with no subscripts on it was the degrees of freedom for that specific object. And it looks like at some point it became a coupling. I'm not sure if it's always been a coupling, and I was just confused.
Yeah, when I put gx and gf, those are couplings. So I guess I'll write fx/f here. Yeah.
Okay. So like the g's over there, the no subscripts, those are degrees of freedom?
Yes.
Okay.
Yeah.
Thank you. Sorry.
Yeah, those are degrees of freedom. Yeah. Okay, so that's the heavy mass limit. The next thing we can say is also known as the lead Weinberg bound. roughly speaking. Which is, if we take this first scenario where the vector or the mediator is heavier than the dark matter, and let's just say that the mediator is a standard model mediator, so it has to be of order weak scale, or we'll just consider a weak scale mediator, put mz to the fourth. So as the dark matter mass is lowered compared to the Z mass, this annihilation cross-section gets smaller and smaller and smaller, and that would lead to a too much number density or too much energy density today. So let's say we keep lowering the dark matter mass, and we try to raise the couplings to compensate that. So again, I'm going to just say, let's say we can make all these couplings order 1. I'm still going to get a suppression with the dark matter mass. And if I set this equal to the desired value here, 10 to the 9 GeV squared, this becomes I can replace this with roughly, I'll write it, mz squared over about 10 to the 5 GeV, 10 to the 4, 10 to the 5. And since this is about 100 GeV, when I divide these two, I'm going to get an order 1 number times GeV, so GeV. So when I hit dark matter masses of about a GeV, the annihilation through weak scale mediators becomes too small compared to what we need for the relic abundance, and we would have too much dark matter. And so the Lee-Weinberg bound says that annihilation, well, they specifically considered some sort of heavy lepton, but if I look at annihilation through a Z, the dark matter mass has to be greater than about GeV. Z Higgs, let's see. So we're getting to the point where we see that if we want to consider the full range of thermal relic dark matter, it doesn't look like we can do it through weak scale interactions for sub-GeV dark matter. Is there anything else I can do with it within the standard model?
So this is predicated on some sort of naturalness assumption that the gauge coupling is order 1.
It does assume that I have a perturbative theory where I can calculate things, yeah. Are there any other mediators I could consider? So Higgs, I've sort of included here because I'm saying it's a similar mass scale as the Z. Photon, yes. There's one more case, the photon. That's not excluded, so I could have dark matter interacting through the photon. It's not excluded by this Lee-Weinberg argument.
Doesn't that kind of counteract the whole idea of dark matter? It doesn't couple into electromagnetic field. That's why we can't see it.
Right, so one might say dark matter should not interact with photons at all, but we could consider the fact that it could be a millicharged dark matter candidate. So it just has a very small coupling with photons. Okay, so we're trying to see if there are any possible ways to get sub-GeV candidates with just kind of standard model interactions. And I'm not going to specify exactly where I get this millicharge from. Just assume that I have some millicharge, so now it's this is E, this is E, and I'll call the millicharge Q, some very small number. And if Q is very small, then we see that this process should dominate over the direct annihilation into the photon, because this one goes as Q to the fourth. So let's see what millicharge we need to get this to work out. So again, the cross section is now, I can just use alpha for convenience. Alpha squared, Q squared. So that means, again, setting this to my 10 to the 9 number, 10 to the 9 GeV squared number. And let's just make the dark matter mass about a GeV to see if this works. So then Q is equal to about, well, I'll make this 10 to the 4. Sorry, 10 to the minus 3. So I get about 10 to the minus 3 times the dark matter mass over GeV. So in principle, I can annihilate through the photon. I just need a very small millicharge, which as I go to lighter and lighter dark matter masses, I just reduce that millicharge. Okay, and so as was brought up, this kind of goes against our intuition that dark matter is dark. So what are some ways we could constrain this millicharge? Is this kind of millicharge allowed if we go to GeV or even lower masses? Yes, I turned alpha squared into 10 to the minus 4. Did I multiply correctly? Yes. Yeah, sorry. So then this becomes 10 to the 5 on this side, and then I'm, yeah, around 10 to the minus 3. Does it seem legitimate to you to have such a millicharge? No. Why not?
For one thing, I feel like normally when you have something that's a fractional charge, it's not stable alone. So like the quarks, you don't get, they don't like sitting there alone. You don't really normally observe something that's stable and has a fractional electric charge.
So in principle, if, sometimes with these fractional charges, I mean, you get attractive forces with other charged particles. But if it's very small, then there may not be any bound states. And they're not neutral bound states. And you can also produce both X and X bar, so you have an average neutral density in the universe. So that's not necessarily a problem. Any ideas how to constrain this?
I mean, the electric force is a long-range force. We know that gravitational interactions are the dominant force for dark matter in ranges. So having a bunch of millicharged objects floating around seems like you have, even for really small charges, you don't allow the gravity to interact.
Right, so yeah, the comment is we have a long-range force, and that's a good observation, and that can overwhelm the gravitational interactions. So we need a probe in order to test those long-range interactions, yes?
We know that dark matter is a halo, and if you were charged, you could start radiating and collapse into a disk, something like that.
Yeah, so one way you could do it is by looking at halo dynamics, definitely. Other ideas?
All is going to have some amount of scattering of light, so for a telescope, I can see these weird clouds.
Good, so we have scattering with light. Yes, so it would interact, so it could scatter with light, like you said, and the CMB could test whether it scatters off light and whether it scatters off of other charged particles. Right, so yes. Also good, we can produce this at colliders, yes, absolutely. So these are all relevant constraints that are that make this scenario very hard. I'm just going to discuss one briefly to show you why this freeze out mechanism does not work. Unless there are other things anyone wants to discuss. So this case, as we discussed, there's scattering off. So you can just do direct Thomson scattering. So let's say gamma. Here's my dark matter and gamma out. And that will affect the CMB. But because of the scaling, this is not a long-range interaction. So actually, the one where I scatter off of, say, protons is actually a stronger constraint on this millicharge scenario. So I can scatter off of protons, and if this is effective at CMB recombination times, then that would affect, the CMB. It would lead to additional, say, polarization. It can also lead to damping in the temperature spectrum. It can also prevent the dark matter itself from clustering if it's scattering off of the baryon fluid. So let's estimate this process. And there are lots of different reviews, by the way, with constraints on millicharge dark matter. Here's one of them. So again, we want to compare this, estimate this cross-section times number density for a rate compared to Hubble at the time now. By the time of, say, when structural formation happens, which we saw last time was around keV, for instance. So this rate goes as the number density of the baryons times some cross-section, which goes as the millicharge squared alpha squared over t squared. Okay, so now I don't have the mass suppression because this is a scattering process and not an annihilation process. The number of baryons can be written in terms of the number of photons because we know that the baryon to photon ratio is about 10 to the minus 10. Okay, so I compare this quantity versus Hubble. At temperatures of about keV. So keV is very small. This number on the right is going to be very small. And I'll just give you what the number is. It's about 10 to the minus 26 GeV.
That's what temperature?
At T of around a keV. Or I think this specific number is T around 0.1 keV. So remember what we saw last time was structure formation has to start happening around keV temperatures. And so if this process is effective, then we have kind of the collisional damping effect. So the Hubble expansion is extremely small because of this M Planck. It's 10 to the minus 26 GeV. And on the right, the annihilation rate, or sorry, the scattering rate goes as the temperature. This is about keV. And I get a suppression of 10 to the 10 from the baryon to photon ratio. But, sorry, I'm moving this up and down because I know the bottom's a little hard to see. But if the millicharge is 10 to the minus 3, this number on the left is still going to be way bigger than the Hubble expansion. Right, I'm still going to get of order 10 to the minus, so this gives me a 10 to the minus 4, 10 to the minus 6, and then this gives me another 10 to the minus, well, it gets pretty close actually, so I think it was like 10 to the minus 24, 10 to the minus 25 GeV on the left. But it's still going to be bigger than the Hubble expansion. And this constraint then rules out the entire mass range for sub-GeV dark matter that gets its relic abundance by having, by annihilating through a photon.
Just the very last sentence you said.
Yes, no problem. So the conclusion was that scattering of the dark matter off of protons, this process can be quite large if dark matter is millicharged, and so it rules out the entire freeze-out. It rules out the freeze-out scenario for dark matter that's millicharged and lighter than a GeV.
Wait, so, I mean, if we decrease the mass, we're decreasing the interaction rate.
Mm-hmm.
Don't we want the interaction rate to be smaller than the Hubble scale at that temperature?
Yes, you're saying we just keep reducing the dark matter mass. You can keep reducing it. There are other constraints that then start to kick in. Yeah, you can keep reducing it, but there's another CMB constraint, which is that you can look at the inverse process, proton scattering off of the dark matter, and that affects the CMB. So all of these things come into play, and it does rule out the entire freeze-in. Also, direct collider searches, as someone mentioned, will rule this out as you go lighter. Yeah. Yes.
Why did you pick 0.1 keV?
I picked a 0.1 keV because I know that structure formation has to start by then, and I want this process to decouple well before 0.1 keV.
And if you decrease the mass, presumably, you will also decrease the time at which you will freeze out.
So your question is if I just
I mean, if you make that the mass much smaller, maybe you start freezing out very late.
yes.
That's a lot of time. So you want that matter to happen via BBA.
That's right. So the comment is, if I make this much less than MEV, then I might worry about BBN as well, and that's definitely also true. So that's another consideration. So we said yesterday during Dan's lecture, if this mass is less than 10 MeV, it's still in equilibrium with electrons and positrons, then that's going to be bad for BBN, and I'll go more into that in the next lecture as well. Okay, so the reason I've gone through this series of exercises is because we've now shown that if I have a sub-GeV thermal relic, I have to introduce a new light mediator. I cannot annihilate through any of the standard model mediators. I have to introduce some new vector, which is sufficiently light that some of these annihilation processes are effective, and the dark matter is sufficiently dark. And this has been one of the big motivations for sub-GeV dark matter. Because it implies the existence of this new light mediator, that also has all sorts of experimental and observational implications. Okay, and let's just outline a couple of these. We'll go into a lot more detail about them later. One is structure formation. Although the mediator is light enough that we can satisfy these kind of CMB bounds, this new light mediator allows processes like dark matter self-scattering, which is larger because the mediator is light. And that can affect your halo dynamics and introduce new effects on small scales. And that's a particularly exciting area where people are trying to understand what exactly dark matter does for the reasons I mentioned last time, and to look for effects like this. If I have new light mediators, then I can have all sorts of different accelerators / collider searches that are different from the kind of signals that would traditionally be looked for if you're talking about SUSY, for instance. So we have things like high intensity accelerator experiments / fixed target, where you can focus on having a low energy but a very high luminosity, so that you get so that you're more sensitive to these new light mediators. And by light, I'm sort of mean around a GeV or less. But it could be, the boundary, as usual, is a little bit fuzzy. And a third thing that I'll spend a lot of time on is that the direct detection signals are also quite different, can be quite different. So both that we have light dark matter, which makes the direct detection challenges different, and also because when you have these light mediators, they change the kind of phenomenology you get, they change the recoil spectrum. You can also have inelastic scattering and so on. Okay, and the fact that these are all that this thermal relic scenario with light mediators is so far relatively unconstrained, and yet has all these different exciting experimental probes, has driven a lot of the activity in the field lately.
Question?
Yes?
It occurs to me that if it is to annihilate through this, not just self-scatter through this light mediator, that means that this new light mediator also has to couple to the standard model particles, which would be some sort of interesting other force that would be being mediated by this, and I feel like that would be of itself observable.
Exactly. So I was just about to comment on that, so thank you for bringing that up. So given that there's a new light mediator, we know that it probably has to be relatively weakly coupled to the standard model in a way that we'll quantify later. And so this has led to this picture you may have seen of dark sectors where I have some standard model. Here I have my dark matter and I have my mediators, whatever they are. And they have to have a pretty small coupling to the standard model. So this is kind of my portal, which says that there's a pretty small coupling with the standard model. Definitely the interactions have to be weaker than our standard model interactions. In the next lecture, I'll address whether we absolutely need a coupling, observable coupling of this mediator. But the point that was brought up is that if we are considering this possibility, we don't have to focus on just dark matter searches. We can just talk about searching for this mediator if it has a coupling to the standard model. And that also goes, for instance, under this accelerator search, direct accelerator/collider, direct mediator searches. And it's as a generic possibility for extensions to the standard model. Okay, so I'm going to draw diagrams for a couple of the canonical benchmarks, and we'll start going over the model building aspects for those benchmarks in the next lecture. Yes.
So you're saying light measure graph or has long graph example card.
Mm-hmm.
So in this instance, how do you catch that dark matter can still connect or equilibrium with
Right. So yeah, the question is it it's not very obvious that I can get a large enough cross section. Sorry, not for this process. I can get a large enough cross section for annihilation while being consistent with already the existing bounds on the light mediator. That's the question, right?
Yeah, I was saying the elastic extent the dark matter and the thermal particles,
Yeah.
right? Large enough to keep the dark matter is connected with the moment.
Yeah, so we have to check that the dark matter can be in equilibrium with the standard model thermal bath and that it satisfies all these constraints. It's not obvious. We have to go through and look at these constraints. Absolutely, yeah. But the short answer is it works out that there's parameter space for these thermal relics, which is not excluded by any existing constraints. Okay, so the benchmarks for this sub-GeV dark matter I'll consider. By benchmarks, I mean I'll consider a couple of different annihilation processes being the dominant process. So one is direct annihilation into E plus E minus through, well, I'll introduce later, is a dark photon. This is kind of the this is direct annihilation. This is sort of what we usually think about in the thermal freeze-out case. There's a scenario we talked about where we can annihilate directly into these mediator particles. That's called secluded. So this process sets theoretic abundance, and I do need to do something about these mediators such that they kind of go away and don't affect the cosmology at late times. That introduces a standard model coupling, potentially. And I'll also discuss freeze-in, which we also commented on in a previous lecture, where I have E plus, E minus, through my light mediator to X. So only this process is really happening. It's happening at a small enough rate that the dark matter is never populated thermally, and so the reverse process doesn't happen very effectively. And we saw a cartoon of that last time, where if this is freeze out, then this is freeze in. And despite the fact that this process for this to be true, for this process to only happen in one direction, the couplings have to now be really, really small. So you might think that this scenario is really hard to test, But because my mediator is light, I actually get a pretty large signal in direct detection experiments. And so that's why I'm also introducing this freeze-in scenario. And just to say, there are definitely more that I'm not going to talk about for and on, things like SIMPs and so on. But I'm just going to use these to guide the discussion about the phenomenology and the cosmology of these sub-GeV sectors. Okay, and so that's it for today. I'm out of time. Any last questions? Nope. Okay, then thanks.